Hello everyone, welcome to the Makri Virtual. Hope you are doing good. Today the class is on new timing. So hope you are comfortable with this timing. Today I'm going to continue with chapter number 3, that is machine level representation of programs. Till now we have covered multiple topics and the last topic is left, that is floating point representation of programs in machine level language. So I'm continuing with this one, but before that let's take a quick review of the last class, that is previous class, what we have covered in the last class. So let's take a quick review of the last class. In the last class we have discussed about the x86-64, how x86-64 works. It is also known as x64, x86_64 and AMD 64 because it is developed by AMD, that's why it is known as AMD 64, and it is of 64 bit, that's why its name is its name is ending with 64, that is x86, that is a bulb, and 64 is the bits, means how many bits are available? 64 bits. As the name advised, and it is said, it is a 64-bit version of the x86 instruction set. It supports vastly large amounts. Large amounts means because it contains 64 bits. So there are total how many bits? That is 2 part 64 bits. As it contains 64 bits. Then we also discussed multiple virtual memory, means how virtual memory operates and how virtual memory works. And this is the paragraph which have been said about the history of the x86-64, that is, it was created by AMD and then been implemented by AMD, Intel, VIA and others. It is of multiple bits, that is 16 bits, 32 bits. Then we also discuss about the history of AMD, means how it is developed by AMD and how it is created by AMD, and that is how AMD works in a flow, that is history of AMD. So this is AMD64 was created as an alternative to the radically different IA64 architecture. IA means Intel architecture, that is alternative, or that is obsolete and that become outdated, and the new version is AMD64. So AMD64 replaces the IA64 architecture. This is the whole paragraph says how AMD works, in a picture, comes in the picture. First of all, it comes in 1999, then August 2000, then it is an Intel approach of creating an entirely new 64-bit architecture with IA64. Now, this is the important line. The first AMD 64-based processor, the Optane, was released in April 2003. Then we also talked about the architecture of the x86-64. Architecture means the structure of the x86-64, means how it works and what is the internal layout, what is the level of the instruction to the CPU, or how it is behaved, or what is the structure of x86-64. This is assembly language is the lowest part of instruction to the CPU without actually entering into the machine code itself. So the main crux or the main paragraph is saying that x86-64 is used as a architecture, is used as a 64-bit in which there are multiple parts, there are multiple architecture that is developed by AMD, or that is used in AMD and Intel processor. These are the processors name, that is AMD and Intel. So x86-64 refers to a 64-bit architecture that is used in AMD and Intel processors. It is an extension that is developed for the 32-bit x86 platform. That is, it uses 32 bits and uses x86 platform for developing the architecture, for using the architecture. Then next point says there are so many instances, means there are so many examples by which we can use x86-64 version. And there are so many topics that is available that deals with how hardware capability, what is the hardware capability that is used for x86-64 architecture. Then we also studied about the different features that is available for x86-64. Means what are the features, what are the qualities that is x86-64 provides. The one of the main feature is that it is of 64-bit integer capability. Means the capability for this, or the capability of x86-64 is a 64-bit. As the name advises, 64-bit. So it has a capability of 64-bit, that is, it stores maximum of 64-bit registers, and all arithmetic and logical operations, memory to register and register to memory operations, can be operated on the 64-bit register. Means every operation, whether it may be arithmetic operation, whether it may be logical operations, all the operations must be carried on 64-bit integers. Then the next feature is that additional registers. There are so many additional registers available in x86-64 along with the or in addition to the general purpose register. For example, EAX, BAX, EBP, ESP, ESI, EDI. And the multiple registers that are using that convert or increase from 8 to the 16. That is increase from RAX, RBX to R8, R9, R10 and so on till R50. So there are 8 more registers that is added, starting with R8 and ending with R50. Then next feature is that larger virtual address space. Means whenever we use x86-64, so it has a larger address space or larger virtual address space, so that it works or it performs the operation, that is larger virtual address space. Then next point is larger physical address space in legacy mode. Then last one is instruction pointer relative data access. Means we can access the data with the use of RIP, that is relative to the instruction pointer register. So these are the striking features that is available or that is provided by x86-64. Then we also talked about the data types. What are the data types available in x86-64? These are the multiple data types. This is char, short, int, unsigned, long int, and this is of Intel data type, that is byte. This is of x86 size. How many bytes required? That is 1 byte, 2 byte, 4 byte, 4 byte, 8, 8, 8, 4, 8, 16. And these are the multiple C declaration. These are the Intel data type, and these are the x86-64 type or bytes. Then we also talked about the multiple features of data type. Means what are the advanced features, how it converts from IA32 to x86-64. So these are the multiple features that is provided by x86-64. The main feature is that it is expanded, or the registers are expanded from 8 to 16. Then first point says it is of 64-bit. As I told you, integer arithmetic operations support 8, 16, 32 and 64-bit data types. Then we also talked about the multiple arithmetic instructions that is available in x86-64. There are two types of operands. One is destination and one is source. And multiple registers are used for the destination and for the receivers. So this is your addition operation. First one is your addition operation, that is ADD, add, SRC, DESP. That is add source to the destination and put the result to the destination. Means it add both the number, but it put the result in the DESP, that is destination. Another one is add DESP SRC, adding all the values or both the values and put the results in SRC. This says this adds SRC to destination. If you are using the NASM syntax, then the result is stored in the first argument. If you are using the GAS syntax, it will be stored in the second argument. This is your inter syntax, this is your GAX syntax. In the same way, we have also talked about the subtraction, means how subtraction takes place among the source and the destination. These are the multiple MUL, that is multiply argument registers. This is your division registers. Then this is your increment. How we are using increment? By using INC keyword, and the ARG is your argument. Argument means any type of argument, any type of operand, any type of operation. In the same way, we can decrement by using the DEC, then ARG. Then we also talked about the control, means how controlling is done by x86-64. So there are two new additions as compared to the IA32. The new additions are CMPQ and TestQ. This is used for compare quad words. This is used for test the quad word. So one is used for comparison and one is used for testing. In the same way, there are multiple conditional move instructions also which are used by conditional operator. This is a conditional operator. This is the variable. V is the variable that stores. Why it stores? Because equal to sign is used. So V equals to means the output of this is stored to the variable V. So this is V equals to text expression. Means how we are using the text expression. What is the scenario? That is text expression, then question mark. This is your first expression. If this condition is true, then use this one. Otherwise is denoted by colon. In the same way, we are using if else. If the condition is true, this statement will execute. First one, else. Else means the colon, next statement will execute. So this is how we are using the conditional operator. And the output of all this is stored in the variable V. In the same way, it is shown if test expression go to else. If not equal, go to direct else. Otherwise, print the first expression, that is then expression. Go to done, that is finish. This is finished part. So I am repeating again. Test the condition. If the condition is true, execute this part. Otherwise, execute this part. Then we also talked about the procedures. Procedures are the chunks or the small programs that is a part of the main program, and it is also used with the x86-64. Then we also talked about the argument passing, means how we can pass the argument via registers. Then how we are using the stack or with the use of x86-64. Means how we are using the stack operation, that is your push and pop operations while using the x86-64. That is your stack frame. There are multiple reasons why a function may require a stack frame. These are the multiple reasons. First reason is that there are too many local variables to hold in registers. That's why we need the push operations. Because there are so many local variables, there are so many variables that are used to hold the register. Then there are so many local variables are arrays of structure. The functions uses the address of operator to compute the address of a local variable. So in x86-64 we are using a stack. The main reasons are this one. The function uses the address of operator, that is your ampersand. Then the function must pass some arguments on the stack to another function. The function needs to save the state of a wholly save register before modifying it. So that's all for yesterday's session. Now I'm going to continue with your next topic, that is floating point representation. So let's start with the new topic. This is your main topic, that is machine level representation of floating point programs. Till now we have covered only machine level representation of integer points, means integer values. Now next topic is that how we are representing or how we can represent floating point number in machine level programs, or how we are using machine level representation of floating point programs. This says, thus far we have only considered programs that represent an operator integer data type. As I told you, till now we are using only the programs that operates on integer values or integer data types. In order to implement programs that make use of floating point data type, we must use some method of storing the floating point data and additional instructions to operate on floating point value. This says, to make the floating point or the floating point number operational, we are using or we are having multiple floating point data and additional instructions so that we operate on floating point values, and they are used as machine level representation. We also require convention on how to pass floating point values as function argument and to return them on function results. So this paragraph says, now it's the time to focus on the function points or the floating point number so that we can perform the operations with the help of floating point numbers also. Because it is not mandatory that we are every time we are using integer points. No, it is also time when we are using the floating point number. So this is the important topic, that how we are using the floating point number and how we can represent the floating point numbers. Now let's see with the help of PPTs. This is the 8th PPT. Yeah, this is the correct. Floating point. First of all, what is a floating point? In computing, means in computers, floating point describes a method of representing an approximation. Approximation means round of figure of a real number in a way that it can support a wide range of values. Means we can represent, or we are representing floating point as a, or we are considering floating point as a method of representing an approximation. Approximation means a round of figure of a real numbers. A round of figure of a real number so that they can communicate with each other, or so that they can communicate in an effective manner, and they support a range of values. The numbers are in general represented approximately to a fixed number of significant digits. That is a significand or significant, and the scaled using a exponent. So there are two parts. Numbers are represented as a fixed number as a significant, and the scale, that is decimal number, are represented by exponent. I am repeating again. In floating point, the real numbers are represented by significant, and the decimal numbers are representing using the exponent. The base for the scaling is normally 2, 10, 16. Base means whatever the base. This is the base. This is the syntax. Base may be 2, 10, 16. Because as I told you, there are generally there are 4 types of number system, but generally we are using 3 types of number system: binary, decimal, hexadecimal. So 2 has a base of binary, 10 has a base of decimal, 16 has a base of hexadecimal. So we are using only 2, 10 or 16. The typical number that can be represented exactly is of the form. This is the syntax. First one is your significant digit. This is not significant, this is significant, this is T. Significant digits into base exponent. This is your integer part, this is your base, this is your decimal part. Means decimal part is represented by this part and integer part is represented by this part. So this is your floating point. Next, say a floating point number or real number can represents a very large means there are a huge number that is available in floating point, because these are represented by exponent. So we can represent, or we can give any number of values, any huge values in with the help of floating point numbers. So it can represent a very large, that is 1.23 into 10 power, this is power, or this is caret, or this is power 88, or a very small, that is 1.23 into 10 power minus 88. Means we can represent the number in a large manner or in a small manner. This is a large quantity and this is a small quantity. This is a large quantity. It could also represent very large negative numbers. So this is also a facility to provide a very large negative number and very small negative number. This is your large negative number and this is your small negative number, as well as 0 as illustrated. So this is your illustrations. First one is your minus 1.23 into 1088, 10 power 88. This is your large negative number. Then next is your 1.23 into 10 power minus 88. This is very small negative number. This is large and it is very far to the 0 and very near to the infinity. So this is very large number. In the same way, this is very close to 0. This is a small negative number, as minus sign and minus of power is used. Then this is 1.23 into 10 power minus 88. This is also very close to this one, because there is a positive sign. This is a negative sign, so comes to the left of the 0, and this is positive, so comes to the right of the 0. This is plus 1, that is, this is minus 1 into 10 power 0, 1 into 10 power 0. Then this is your my 1.23 into 10 power 88, and this is also positive. Exponent is also positive, means power is also positive, so it is near to the infinity and it is very far to the 0. Near to the infinity and very far to the 0. This is how floating point represents. Means it can represent a very large number, very small number, very large negative number, very small negative number. So it can represent large number, small number, negative number, any type of number that is too far, too near, any type that is represented by floating point numbers. Then IEEE, as I told you, IEEE is Institute of Electronic and Electrical Engineers. So this is your IEEE. This is a standard 754 floating point in modern computer. So this is a standard that is IEEE 754 provides a floating point or gives a facility or provides a floating point representation in modern computer. This says the IEEE has standardization the computer representation for binary floating point numbers in IEEE 754. ACA means how we can say IEC 60559. This standard is followed by almost all modern machines. IBM supports IBM own hexadecimal floating point. As I told you, IBM follows its own rule, so that's why it is not using even floating point. We have also discussed that IBM computers do not use integer points. In the same way, IBM don't use floating point representation or decimal point representation. The standard provides for many closely related formats, differing in only a few details. 5 of these formats are basic formats and other are termed as extended formats. And 3 of these are especially widely used in computer hardware and languages. These are the 3 basic standards or basic formats that is available. One is your single precision, double precision and double extended provision. I told you, I discussed with you in last 2 or 3 classes that what is single precision, what is double precision. So let's take again. Single precision usually used to represent the float type in the C language family. So it is used to represent the float type. Whenever we use the C data type that is float, so this is used to represent the C language family. Though this is not guaranteed. This is a binary format that occupies 32 bits, that is 4 bytes, and is significant as a precision of 24 bits, that is your 7 decimal digits. So this is a single precision that is used to represent the floating point data type in C language. In the same way, next one is your double precision that is used to represent the double data type in the C language. And this uses 64 bits and 53 bits as comparison to 32 and 24. Then next is your double extended, that is also known as extended precision. This is a single, double, this is also known as extended precision. This is a binary format that occupies at least 70 and is significant as a precision of at least 64 bits. These are the multiple parts or these are the multiple categories of floating point representation. A format satisfying the minimal requirement, 64 bits, 15-bit exponent, thus fitting on 80 bits. It provided by x86 architecture. I told you in the last class, x86 architecture uses 64 bits. So this is the same line. This is the format that is used by x86 64. In general, on such processors, on such CPUs, this format can be used with long double in the C language family using the C99 and C11 standards. Then next is your floating point arithmetic operations. So this is there are 3 types of floating point that is provided by IEEE. One is the single precision, double precision and extended precision or double extended precision. Now next is your floating point arithmetic operations. This is For ease of presentation and understanding, decimal radix. Decimal radix means decimal number or the decimal base with 7-digit precision will be used in the example, as in IEEE 754 decimal 32-bit format. The fundamental principles are the same in any radix or precision. Means the fundamental are same for any operation. It may be arithmetic operation, it may be logical operation, and it may be addition, division, multiplication, any arithmetic operation. But the base is same, radix is same, precision is same, format is same. Except that normalization is optional. That is, normalize means how we can normalize, how we can use the exponent, how we can shift the bits from one place to another. That is different. But that does not affect on the result. That gives the same result. Next is, here S denotes the significant and E denotes the exponent. So whenever I am using in example S, that is known as significant, and E is your exponent. Next point says addition and subtraction. So this is your arithmetic operation. How we are performing, or how we add and how we subtract the floating point numbers. This is a simple method to add floating point numbers is to first represent them with the same exponent. Means if there is there are two numbers. One number have an exponent 10 power 2 and the another number have an exponent 10 power 5. So first of all, reach the first number as a 10 power 5 because the second number have a exponent that is 10 power 5. To make the or to reach to the same level, so that becomes the easiest way to perform any arithmetic operation. This says it is first represented with the same exponent. In the example below, the second number is shifted right by 3 digits, and we are proceeding with the user addition. The second number is also shifted by 3 digits. Now let's see example. This is your 1, 2, 3, 4, 5, 6, 7, and this is your 10 power 5. So these are this is represented by 10 power 5. This is 10 power 2. Now this 10 power 2 now this 10 power 2 is also used this 10 power 2 and this is 10 power 5. Now I have to convert, or I have to match, or I have to make the same exponent. This is 10 power 5. So converting this number from 10 power 2 to the 10 power 5 by shifting 3 digits, because this is 2, this is 5. So when I shift 3 digits, then it becomes 10 power 5. So I am shifting 3 digits. Shift from this to this. This is the 3 digits add and shift it from one part to the another part. So this becomes 0.000. This is at shifting of 3 digits, and 1017654. So the first step is that first of all same the exponent part, that is 10 power 5, 10 power 5. It is 10 power 2, then right shift by 3 digits. 3 digits why? Because the 2 and the 5 difference is 3. So it is adding, or it is shifting from left to the right. Then there is a addition. Now next part is where do the addition. Hence this equals to this equals to this into this. As I told you, this is this value, and next one is here this value. Now it is the same, but this is represented by this one, as I shown you in the example. This is this one. Now exponent part is same, so take the common as the exponent part. This is your common, that is 10 power 5, and these are the internal parts or the same part. This is common, this is this one, and this is only one time because this is separated as common. Now add these two values. This is 1.2345667. This is 1.234. This becomes 41 plus 5. Then addition of these numbers. So this is the value after adding this. So how it proceeds or how we can add the floating point number? First of all, make the same exponent. Whenever we want to make the same exponent, simply right shift the bits by number that you want to shift or by the number that you want to increment in the exponent. Then adding the two values. How we can add? By taking the common of the same or the similar exponent, that is 10 power 5, and this is added, and then in brackets the numbers are added. In brackets the floating point number or the significant are added. So this is how the significant are added. This is the same, so the output is this one. I think this is clear to you. Now, next is that it is in detail how it is used and how we are using this one. This is in detail. This one. After shifting this one, the sum becomes this one. As I told you, the actual result is that is this. Now, next is your. This is also in detail. This is the same slide. Now, note that the low 3 digits of the second operand. This is your second operand, and the low last 3 digits. This is the last 3 digits of the second operand 654 are essentially lost. Why it is lost? Because it is carried forward to the next place. Because we want the result in 8 bits. So this is carry forward or this is discarded. Because this is of 8 bits, 1, 2, 3, 4, 5, 6, 7. There are 7 bits, not 8 bits, there are 7 bits. No, these are 8 bits. 1, 2, 3, 4. Yeah, 8 bits. This is also of 8 bits, but the output is more than 8 bits. So we are discarding the leftmost or the rightmost or the most significant bit. So the output is 1.235584 because this contains 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So this is this says the last part are going on because the input digits or the input bits are less than the output bits. Then how to multiply and how to divide. Next part is the addition and multiplication and division in the same way which I told you. How we can add? By simply separating the exponent part and by separating the significant part. And first of all, making the exponent part same or making the exponent part equal and then adding the significant value. So now, next is your multiplication. To multiply, the significants are multiplied while the exponents are added. This is the most important point. The real numbers are multiplied while the exponents are added with each other, and result is rounded and normalized. Normalized means if there are 7 bits, then the output is same as the 7 bits. If the input is of 9 bits, then the output is same of the 9 bits. That is known as normalized. And round off means if there is a requirement for round off, we can round off the figure by discarding the most significant bit. So now let's start with this example. E is 3, that is exponent is 3, exponent is 5. This is your significant, that is 4.734612, 5.417242. This is your product, means we are multiplying these values. Exponent, significant values, 5 4 is 20. This is the multiplication of this one, this into this, right? Then after rounding, and we are adding the exponent part. This says while the exponent parts are added and significant parts are multiplied. This is the exponent part, these are added, 5 plus 3 is 8, and this is multiplied, this is this one. Now round, and the result is round off, this is round off, E equals to 8. There are 1, 2, 3, 4, 5, 6, 7. 7 bits, so I am rounding off after the 7 bits. This is 1, 2, 3, 4, 5, 6, 7. This is 3, and this is 8. As I told you, whenever we round off, then we see the next bit. If the next bit is 5 or greater than 5, then it is rounding off and it becomes, or it is added to the leftmost bit, that is 3 becomes the 4. This is rounding off and this is e equals to 9. Why this is normalized? Because the addition is of 8 bits and this is adding the new exponent. Then it is shifted to the right hand side. This is 2.564854. Now, first of all, we are adding the exponent part and multiplying the significant part. So the first target is that add the exponent part and multiply the significant part. Then round off the figure by way of input, means how many input bits are available. Then normalize the bits or normalize the value. In the same way, division is also performed. This says similarly, division is accomplished by subtracting the divisor's exponent. In this we are adding, in that we are subtracting the exponent and dividing the dividend significant by the divisor significant. We are multiplying these, and in division these are divided and these are divided with each other and these are subtracting with each other. That is 5 minus 3 and these are divided with each other. So in multiply these are added and these are multiplied. In division these are subtracted and these are divided with each other. Now next part is your character encoding. Before this, let's take a quick review of your book. That is how the floating point representation takes place. So this is machine level representation of floating point programs. This is the theory which I told you. This is x87 floating point architecture. So that's all. Next part is summary, which I told you in the last. So the next part is your character encoding. But before this, let's take 5 to 10 minutes break, then come back and then start with the character encoding. So let's take 5 to 10 minutes break. Let's continue with the next topic, that is character encoding. In computer memory, characters are encoded. As I told you, there is a ASCII character, that is American Standard Code for Information Interchange. So in computer memory, characters are encoded. Characters are encoded in the memory or represented using a chosen character encoding scheme. Character encoding schemes like ASCII, BCD. There are multiple character encoding schemes that are known as character set, char set, character map, code, page. For example, in ASCII, these are the multiple examples of ASCII code. These are the multiple examples of character encoding. The first one is your ASCII, that is American Standard Code for Information Interchange, as well as in Latin 1, Unicode, and many other character sets. Code number 65D, 41H2, 90D. This is the representation of multiple codes, multiple characters, that is 65D. This is represented by 41H to 90D. 90D is your 5AH, that is represented A to H. This is your A value, this is your Z value, right? In the same way, code number 97D, this one is represented or representation for small a to small z. This is from capital A to capital Z, this is from small a to small z. Then code number 48D to 57D. These are used for representation of 0 to 9. That is for representation of the number that is starts from 0 and ending with the 9. That is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That is, there are total 10 numbers. It is important to note that the representation scheme must be known before a binary pattern can be interpreted. So this is the mandatory condition to represent or to note the representation scheme before the binary pattern. For example, you must have a knowledge of the 8-bit ASCII code, BCD, that is binary coded decimal, American Standard Code for Information Interchange. Example, the 8-bit pattern, that is 0100 0010B, could represent anything under the sun known only to the person encoded 8. The most common or the most commonly used character encoding schemes are 7-bit ASCII code. As I told you, there are two types of ASCII code. One is 7-bit ASCII code, next one is a 8-bit ASCII code. These are the most important encoding schemes, that is 7-bit ASCII and the 8-bit ASCII code for Western European characters and Union for internationalization. Means there are two types of ASCII codes used. One is 7 for the 7-bit and next one is your 8 bits. A 7-bit can represent 128 characters because 2 power 7 equals to 128. So this can be used to represent 128 characters and symbols. Then 8-bit character encoding can represent 256 characters and symbols because 2 power 8 is 256. So that is used for representing the 128 and the 256 characters. Whereas a 16-bit encoding scheme such as Unicode can represent 65,536 characters and symbols. This is the character encoding, means how we can encode the characters using various schemes like ASCII, BCD, hexadecimal, binary. There are multiple options. Now, next topic is your integers, floating point numbers and character. Means this is the crux of the what we have studied in the machine level representation of program chapter. This is the summary, or this is the crux, or this is the precise of the what we have covered in the last few classes or last one chapter, that is machine level representation of programs and data. First one is a number system. This is a very easy topic for you because I have studied all these things. Number system means we are using one system organized manner by which numbers are represented in a proper manner or in a systematic or organized manner. That is your number system. In this is written human beings uses decimal, that is of base 10, and duodecimal, that is of base 12 number system for counting and measurements. Probably we have 10 fingers and 2 big toes. Computers uses binary. Binary means binary number that have a base 2 number system, as they are made from binary digital components. Why these are known as binary number? Because they are made up of binary digital components that are known as transistors operating in two states, either 0 and or either on and off, or either 0 and 1. On is your 1 and the off is your 0. So this uses binary number as they are made up of or from binary digital components. In computing, we also use hexadecimal. As you know, hexadecimal that have a base 16 or octal that have a base 8 number system as a compact form for represent binary numbers. So this is the number system which I told you in the first few classes when we have covered about the basics. So this is your number system. Then starting with the first, that is your decimal number system. So much easy topic for you. Decimal number system have 10 numbers, that is from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and known as digits. It uses positional notation. Positional notation means every position or every number has a fixed position. That is, the least significant digit, rightmost digit is of the order of 10 power 0. That is, the rightmost digit as an order that starts with 10 power 0, then the next one is 10 power 1, then next one is 10 power 2 and so on. So this is written. The second rightmost digit is of the order of 10 power 1, that is tens. The third rightmost digit is of 10 power 2, that is your hundred, and so on. For example, 735, that is 7 into, first of all starting with the rightmost digit. This is 5 into 10 power 0 plus 3 into 10 power 1 plus 7 into 10 power 2. So this is the way how decimal number represent. The rightmost digit is multiplied by 10 power 0. The next rightmost digit is multiplied by 10 power 1, 10 power 2 and the digits. Next, 1.1 is decimal that have a base 10. Next is your binary that have a base 2. This says binary number system has two symbols, either 0 and 1 or either on and off, known as bits. It is also known as positional notation. Why it is known as positional notation? Because the position is fixed. Either may be 0, either may be 1. For example, 101, 108. This is 101, 10. So this is 0 into 2 power 0. This is first digit. Then 2 power 1 into 1. Then 2 power 2 into 1. Then 2 power 3 into 0. Then 2 power 4 into 1. This is last one is your B, not any number. This is your digit. So the main digits are 10110. So the rightmost digit is multiplied by 2 power 0. Then next part is multiplied by 2 power 1, 2 power 2, 2 power 3 and 2 power 4. So we shall denote a binary number with suffix. This is your suffix. So this says we shall represent or we are representing or we may represent the binary number with the suffix. Some programming languages denote binary number by suffix or prefix, that is 0b. This is 0b and there is a binary number. This is your suffix b, or prefix b with the bit quoted, that is b this one. So most programming languages use the suffix for and prefix for the binary number, and the most common is b because b stands for binary. Binary digit is also known as bit. 0 is known as bit, 1 is known as bit. So the binary digit is known as bit. 8 bits is known as byte. This says 8 bits is known as byte. Why 8 bit unit? Probably because 8 equals to 2 power 3. Next is your decimal number system. Sorry, hexadecimal number system. Hexadecimal number system uses 16 symbols. In decimal we are using 10 symbols from 0 to 9. In binary we are using 2 symbols, that is 0 and 1. Hexadecimal uses 16 symbols, that is from 0 to 9 and then from A to F, that is from 0 to 15. So it first starts with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then 10 is represented by A, 11 is represented by B, 12 is represented by C, 13 is represented by D, 14 is represented by E, and 15 is represented by F. And these are known as hexadecimal digits. So this uses, or hexadecimal uses 16 symbols, that is from 0 to F. First of all, 0 to 9 are the digits and from A to F are the characters. And these are known as hexadecimal or hex digits. It is a positional notation. For example, A3EH. So H is not any number, E is 14. So 14 into 16 power 0. H is used for representing the hexadecimal. This is the prefix or the suffix. This is suffix, not prefix. Suffix is also represented or available at the end, and the prefix is available at the beginning. This is your suffix A3E. E has a value 14, so 14 into 16 power 0 plus 16 power 1 into 3. Next is your 3, then 16 power 2 into A. A has a value 10. This is the representation for the hexadecimal number system. We shall denote a hexadecimal number, in short hex, with a suffix. This is a suffix. Some programming languages denote hex numbers with prefix 0x. So this is your prefix and this is your suffix. H is your suffix and 0x is your prefix. Example, 0x, 1a, 3c, 5f, or prefix H with the hexadecimal. This is your prefix, this is your 0x is your prefix. So hexadecimal is represented by the prefix or the suffix and using either X or using either H. Next line says, each hexadecimal digit is also known as hex digit. Most programming languages accept lowercase from 0 to F as well as the uppercase. Means the hexadecimal number is not case sensitive. We are using either capital letters or we are using either small letters. Next point says computers uses binary number in their internal operations as they are built from the binary number or binary digital electronic circuits. So this line says computer generally uses or mostly uses binary numbers. Why? Because they are internal to the operation or their internal operations, or they are used for internal operations as they are built from binary digital electronic components. As there are multiple binary electronic components, so these are developed or these are built using the binary component. That's why mostly computers or every computer uses binary number system. However, writing or reading a long sequence of binary digits or bits is a cumbersome or it's a difficult task and error prone. Means there are more chances of error. So hexadecimal number system is a compact form or shorthand for binary bits. This is used as compact form or the shorthand for binary bits. Each hexadecimal digit is equivalent to 4 binary bits. So this is your next point, that is each hexadecimal digit is equivalent to 4 binary bits, that is shorthand for 4 bits as follows. This is your 0H, 0000, this is 0D, 4H, 1H, this is a representation. 2H, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E. This is a representation of binary numbers. Next, 1.4 is your conversion from hexadecimal to binary. Now, it's a good time to recall everything. How to convert hexadecimal to binary? First of all, uses every bits or uses every hexadecimal digit. For example, 10. 10 has a value, A has a value 10. So first of all, convert 10 into the binary. How it will be converted? Just by dividing by 2. Just by dividing by the number 2. So first of all, 2 5 is 10, that is 0. Now I will explain you with the help of pen. Suppose I have to use 10 because A have a value 10. So using 2, 5, 0, 2, 2, remainder 1, 2, 1, remainder 0, 2, 0, remainder 1. So the output is 1 0 1 0. This is the same output 1 0 1 0. Next, using 3. In the same way, used for 3, this is 2 1 1 2 0 1. So the output is 1 1. But we are using 4 bits, so I am preceding or I am using 2 zeros also. So this is 0 0 1 1. Next is your C. C has a value 12. So this is 12, 2, 0, 3, 0, 1, 1, 0, 1. So this is 1 1 0 0. 1 1 0 0. In the same way, I am using 5. This has a value 0 1 0 1. This is the how we can convert hexadecimal to binary. Means using or use each hexadecimal digit, that is A, 3, C, 5, and convert them into the binary individually, that is divided by 2. So first of all, A has a value 10, divide by 2. There are multiple digits, and that digit or that bits must be converted into 4 bits. Then 3, that is converted into 4 bits. C, that is converted into 4 bits. 5 is converted into 4 bits by dividing by 2. So first of all, 10 has number that is divided by 2 and prints the output. 3 have a number that is divided by 2 and prints the output. C have a value 12. First of all divided by 2 and then uses the bit for 4 bits for dividing the numbers. Then there is a number 5 that is divided by 2 and prints the output in the form of 4 bits. Next is your 102A. 1 has a this value, 0 has a 0000, 2 has a this value, and A has a value 10. So the same output 1010. And last one is your B, because this is in binary form and this is in hexadecimal form. This is H, this is B. Next is your conversion from binary to hexadecimal. Now the same concept. First of all, pair of 2 2. Make the pair of 4 4. This is your B. So 4 pair is first one this one 1 0 1 0. Then 0 0 1 0 0 0 1 0. Last one is your 0 1 0 1 and put 2 zeros extra because this must be converted into 4 bits. So put 2 zeros extra, that is 0 0 1 0 0 1 0 0 1 0 1 0 in binary format. Now convert these into the number system, or convert these into the decimal number system. So first of all 0 0 1 0, that have a value 2. 0 1 0 0, that have a value 4. 1 0 1 0, that have a value 10, and 10 is represented by 4. Now let's see how these are converted into this form. First of all 2. First of all 0 0 1 0, not 2, 0 0 1 0. First of all using 2 power 0 into 0 plus 2 power 1 into 1 plus 2 power 2 into 0 plus 2 power 3 into 0. So I'm using 0 plus 0 plus 2 plus 0, that is your 2. So this is how it is converted into the decimal form. This is 2. In the same way, this is converted into 4. This is converted into 10. Now let's see about the 10. That is 1010. This is 1010. So I'm using this one. 2 power 0 into 0. 2 power 1 into 1. 2 power 2 into 0 plus 2 power 3 into 1. So that is your 8 plus 0 plus 2 plus 0, that is your 10. So this is the value 10, and 10 is represented by capital A. That's why I'm using A. So this is how we can convert the hexadecimal to binary and binary to hexadecimal. Now next, conversion from base R to decimal. That is any base to the decimal point. Same way we are using this one. This is from hexadecimal to decimal. We are using 16 power 0 into 2, 16 power 1 into C has a value 12, 16 power 2 into 1, 16 power 3 into 10. Why A has a value 10. That have a value 41410. Then next is your 10110B. This is your binary. This is converted into this one. First of all 2 power 0 into 0, 2 power 1 into 1, 2 power 2 into 1, 2 power 3 into 0. That is not showing over here because that have a value 0. Whenever we multiply anything with a 0, the output is 0. Then 2 power 4 into 1. This is 16. This is 4. This is 2. 16 for 4, 20. 20 plus 2 is 22. This is the 22. This is how we can convert from any base to the decimal. Base R means any base. It may be binary, it may be hexadecimal, it may be octal, it may be any base. That is converted into the decimal form. Now, how to convert any decimal form to the any base? That is your next topic. Till now, this is from any base to the decimal. Now, any decimal part to the any base point. or the decimal part to the any base point. This is use repeated division remainder, for example, to convert 261D to the hexadecimal. This is your decimal form. This is your decimal 261 decimal to the hexadecimal. So first of all, divided by, and this is converted into hexadecimal. So first of all, divide 261 by 16. Quotient is 16 and the remainder is 5. Next, again using the quotient, divided by 16, the quotient is 1 and the remainder is 0. Again using quotient 1, divided by 0, divided by 16, quotient is 0 and the remainder is 1. Now represent this in the bottom to the top fashion, that is 105, and this is the hexadecimal. This is how we can convert from decimal to the any base. This is example from decimal to the hexadecimal. Now next is conversion of this base 4 to the base 3. This is 1023. This is divided by 3 because this is converted into base 3. 25 decimal remainder 0. 28 decimal remainder 1, and so. Now next is your general conversion between two base system with fractional point. Now this is the time for fractional point. As I told you, separate the integer part and separate the fractional part. Means first of all, separate all the integer part and separate the fractional part. For the integral part, means for the integer part, divide the target radix repeatedly and collect the remainder in reverse order. As I told you, separate first of all the integer part as well as the fractional part. Then divide the integer part or divide the radix part in a repeated manner till that the remainder is become 0 or the remainder becomes 0. That is, divide the target and collect the remainder in reverse order. Then for the fractional part, multiply the fractional part by the target radix repeatedly and collect the integer part in the same order. In this in reverse order, this is in same order. This is for integral part, integer part, this is for fractional part. So now let's see decimal to the binary form. First of all, the integer part is 18 and the fractional part is 0.6875. This is 18D. Now divide by 2. By 2 because it is converted into binary. So first of all, 18 by 2, that is a quotient 9 and the remainder 0. 9 by 2, quotient 4, remainder 1. 4 by 2, quotient 2, remainder 0. 2 by 2, quotient 1, remainder 0. 1 by 2, quotient 0, remainder 1. And stop. This is 18D equals to, this is the integer part only. 18D equals to 1 0 0 1 0. This is 1 0 0 1 0. Now next is your fractional part, that is 0.6875D. That is your decimal part. First of all, convert by 2 or multiply by 2. Why multiply by 2? Because it is converted into the binary form. This is 0.6875 into 2. That is a 1.375. Whole number is, integer part is 1, so separate 1. Next, using only the fractional part, that is 0.375, again multiply by 2. This is 0.75, the whole number is 0. Again using the fractional part, that is 0.75 into 2, that is 1.5, the whole number is 1. Again using 1.5, again using 0.5 because we are using only fractional part. So 0.5 into 2, that is 1.0, so that is 1. So the output is 1011, starting from top to the bottom. This is 0.1011. Now combine the integer part as well as the fractional part. So integer part as a value 10010. This is 10010. Point. Next part is 1011. This is 1011 binary. This is how we can convert the base system or any base system to the fractional part, or any fractional part to the any other fractional part. Next example, this you have to try. This is 18.6875, means the same example into the hexadecimal. Same way, uses divide into two parts, integer part as well as the fractional part. Integer part is 18D. So first of all, divide by 16. By 16 because now it is going to convert into the hexadecimal number system. This is 18 divided by 16. Quotient is 1, remainder is 2. Then 1 is divided by 16, quotient is 0 and the remainder is 1. Stop over here. So this has output 12, 1, 2. This is 1, 2. Uses from bottom to the top. 1, 2 hexadecimal. Now, fractional part. This is 0.6875 decimal multiplied by 16. Here, this becomes 11.0. So this is stoppage point because again, whenever we use fractional point, any number multiplied by fractional point is always 0. Or any number multiplied by fractional 0 is always 0. This is 11, so the output is 11. That is B, because 11 has a value B. So now, adding up the integer as well as the fractional part. So first of all, this is 12, 1, 2, this is 1, 2, point. This is your BH, this is your BH, binary hexadecimal. This is your output, 12.BH. Now, this is the exercise. You have to complete this exercise, listen carefully. You have to complete this exercise and please submit to me via chat, via email to me all the questions answers, means all the answers of the question. There are only 4 questions and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 questions. 4 questions have multiple parts and this contains 10 questions. So please submit to me latest by Wednesday, that is day after tomorrow. So please complete it within 2 days and submit to me. So that's all for today's session. Now let's see in your book. This is the summary point, how we are using. This is the notes. These are the multiple examples. These are the examples which you have to study. Now, these are the solution to the practice problem. The practice problem that is available at the end of the every topic. Problem 1, problem 2, these are the solutions that is available at the end of the chapter. This is the solution to problem 1, problem 2, problem 3. There are total 52 problems. So these are the multiple problems to a solution to the multiple problems. Right. And this is till 52. Like this one, problem 32, solution to the problem 32, 42, 46, 48, till solution to the problem 53. So there are 53 problems in your chapter and these are the multiple solution to the problems. So now let's take what we have covered in the today's class. In today's class, we have started with floating point. The main topic is that machine level representation of the floating point. Means how we can represent the floating point number with the machine level code or with the machine level language. So first of all, we have studied about the floating point. What is the floating point? Then we also talked about the multiple versions. How floating point represents. These are the multiple representation of floating points. Then IEEE 754 floating point number means the standard, that is IEEE provides the facility to represent the floating point number. So we have also studied how IEEE provides the facility for basic formats as well as for extended formats. There are 3 types of formats. One is single precision, then double precision, and then double extended, that is your extended precision. Then we also talked about the floating point arithmetic operations. Means what are the arithmetic operations that is available or that is used for floating point numbers like addition, subtraction, multiplication, division. So first of all, addition and subtraction. We have studied about how we can add or how we are adding floating point numbers. These are the examples. Then how we are going to multiply or how we multiply floating point numbers and how we can divide the number. These are the multiple steps how we are dividing or how we can divide the floating point number and how we can divide the or how we can multiply the numbers. Then next topic is your character encoding. We have studied how we are representing or how we are representing multiple characters in computer. There are multiple encoding methods. One is your ASCII, then BCD, then ASCII, BCD, hexadecimal. There are multiple options. There are multiple encoding that are used for characters. Then we also studied about the integer, floating point number and the characters format. Means the crux of the what we have covered in the third chapter, that is machine level representation of programs. In this we have studied about the first topic, that is your number system. So number system is whenever we represent any number, whenever we represent the number in computer, that is known as number system. Then we have studied about the decimal number system that have a base 10. That start from 0 and ending with the 9. Then we have studied binary number system that have a base 2 and that is used for binary number system that have a range 0 and 1. Then we have studied about the hexadecimal that have a base 16 that start from 0 and ending with the 15. First of all, 0 to 9 are the digits and then A to F are the characters. That is, A has a value 10, B has a value 11, C has a value 12 and go on till 15 that is have a value or that have a character F. These are the multiple representation of hexadecimal. Then we have talked about the how we are converting or how we convert from one number system to another number system. That is conversion from hexadecimal to binary, conversion from binary to hexadecimal, conversion from any base, that is base R to the decimal point, conversion from decimal to any base, any type of base, it may be octal, it may be decimal, it may be binary, any type of base. Then how to convert any base system with a fractional part. Till now we have covered about the integer part and we have also discussed about the fractional part, that is how we are converting from one base to the another along with the fractional part. This is the example we have discussed and this is the exercise that you have to complete latest by Wednesday, that is day after tomorrow. Now if you have any doubts, then please text the doubts and I will answer you. So thank you so much for today's session. So now if you have any doubt, then please text the doubts. Thank you so much.